Everybody, it's Mr. Gustin back in the physics classroom. Today we're talking about Newton's second law of rotation. We'll do some math, a little demonstration here, but basically today is just a simple practice problem that leads us into more complicated practice problems. And there's a video after this one with a two-body system, a pulley and a bucket in a well. So if you're looking for a more complicated problem, just go to the next video and that's there for you. But this is more straightforward. Can we simply determine a force of friction based on some data we gather from an object? By the way, happy Tuesday. It's Valentine's Day. So I've got a bike tire here. My bike tire is connected on this rather frictionless axle. But it's right here. We're going to give it a spin. All right, so if I give this bike tire a spin, the only way I'm going to be able to bring it to a stop is to let the friction in the axle do its business, and that's going to take a long time. Or I apply a force of friction gently to the edge of it, and that will bring this bike tire to a stop. That kind of hurts if I do it too hard. So our job today is going to be to take some data and figure out how much force of friction does my hand apply on the bike tire to bring it to a stop. Two things to note: my force of friction is applied at the edge of the wheel, so that's an important thing to know. It's not applied somewhere inside at a various radius inside, because then my torque would be applied at that radius and not the actual radius of the object. The other assumption I'm going to make is that this bike tire, I'm going to assume that these spokes have little to no or negligible mass. We're going to call this thing essentially a thin hoop, making that assumption. It's not a thin hoop. If you were going to be checking my physics, actually, I'm going to be wrong, because I'm making the assumption that this is in fact a thin hoop. So let's go ahead and give it a spin. You know what? I actually want to mark this bike tire first. Let's mark it. I'll put a little whiteboard marker on the edge of it just because that wipes off pretty easily. Let's put some whiteboard marker right there so you can all kind of see it in your screen. You see the mark on the tire right there. We'll start it at the top, and after I let it go, we'll just kind of count the number of revolutions that we get once I apply the brakes. So I'm going to wait for it to come around all the way. Oh, I can't even see it anymore. And once it gets to the top, I'm going to start applying my force, and I'm going to start applying now. That's 1, 2, 2.5. Let's say 2.5 revolutions. So we made 2.5 revolutions. Let's take some data. It came to a stop, so final velocity, angular velocity is 0. I said 3 seconds. It did not feel like 3 seconds. It felt more like, I don't know, 6 seconds. So we'll double that right there. And again, it's an assumption. You can go back and check my video if you want and determine exactly how long it was, but that's what I'm thinking. So 6 seconds, final velocity was this, and we said it was 2.5 revolutions. The first adjustment we have to make, or the first conversion we have to make, is converting revolutions into radians. We know that 1 revolution is 2 pi radians. So if I have 2.5 revolutions, 2.5 times 2 pi is going to leave us with 4 5 pi. 5 pi radians was my change in theta. That is my angular displacement. I have angular final velocity. I have no idea what my initial angular velocity is. I guess you could go back and slow-mo the video down while it's moving at its constant speed and figure it out, but we don't need to know that off the bat. We can probably figure this out in a different way. And again, our big question is how much friction did I apply to stop the tire? So we see an outside force. Let's go ahead and start with our net torque expression. So T net, the only force acting on this was the force of friction at a distance of r, which was our radius. That force of friction was acting over here. That was a force of friction from the hand. It was acting perpendicular to the radius of the bike tire. Again, we're assuming it's a thin hoop. So we have T net equals force of friction r. And then over here, we also know it's equal to I times alpha. We discussed that yesterday, that I alpha is Newton's second law of rotation. So as a side note, this is a hoop, which means its I value is going to be mr squared, the coefficient of 1. So here's what I have. Let's think about what are some things I might need in order to figure out friction. Well, friction is something that I'm finding, so that's important to keep there. The radius of the bike tire, I can measure that, so that's good. I'm going to need to know what I is, and I is made up of mass and radius, so I can find those things, the mass of this tire and the radius of that tire. And I'm going to need to know angular acceleration. So that's one of those things I probably am going to have to calculate given my information over here. So let's brainstorm. I know theta. I know final velocity. I know time but I don't know angular acceleration. This is going to be a tricky one. I'm going to have to figure this one out in an interesting way. I don't have any equations that have acceleration in them, that don't have acceleration in them. So I'm going to have to think about, is there an equation that has final velocity in it? And there is. It's on my equation sheet. It's in my packet, but it looks like this. Change in theta is equal to final velocity times time minus 1/2 alpha t squared. It's in there. It's a substitution equation. It's not one of our best equations that we use most often, but it is in there, and it comes from a couple substitution things. But this is an equation we can use, and this ends up being 0. Right? The final velocity here is 0, so we end up with this. We end up with change in theta is equal to 1/2 alpha t squared. And I can actually go ahead and solve for alpha here. Alpha is going to be equal to 2 theta over time. And let's grab a calculator and figure this out. Alpha ends up being 2 times 5 pi radians divided by 6 seconds. We end up with the acceleration being 5.2. Let's say alpha equals 5.2 radians per second squared. That's not an answer, but that is a piece of my puzzle. It helps me figure this out. So then I'm left with, if I rewrite this equation, force of friction times r equals mr squared times alpha, which is now 5.2 radians per second squared. All I need to know now is radius of the object and mass of the object. And actually I can start seeing these radii cancel out, so I'm left with force of friction is equal to mr times 5.2 radians per second squared. Let's take some data. Let's find the mass of this thing, and let's find the radius of this thing. The radius of this thing ends up being, outside, I end up with 61 centimeters divided by 2. Let's call it 30.5 centimeters, or 0.305. So I need the radius. Well, that marker is bad. I made that, actually. That's pretty impressive. I nailed it. Radius is equal to 0.305 meters. And the mass of that gyroscope is probably, let's call it 600 grams. We're going to estimate 600 grams. So now I've taken the mass of this thing. We're going to call it 0.600 grams. A little more than half a kilogram. That's probably what it actually weighs there. And then we're going to look. All right, now let's plug some numbers in. Force of friction is equal to 0.600 kilograms times the radius, which we said was 0.305 meters, times 5.2 radians per second squared. The force of friction ends up being, let's hope it makes sense, 0.6 times 0.305 times my answer of 5.2 from earlier. I end up with a force of friction being 0.95 newtons. This is my answer. This is the amount of friction that I applied. Let's see if that makes sense. 1 Newton is not a lot of force. It's gently touching. There's not a lot going on there. But I want you to imagine at home, like, how much would it hurt if you applied a lot of force to this bike tire? Like, if I'm bringing this thing to a stop and I'm spinning it and I slam my hand on it, I get, ow! That's going to give my hand like a rug burn, right? It's going to burn my hand. So how much force did I apply? I was gently touching this thing. Very little, bringing it to a nice smooth stop. It wasn't a herky-jerky stop. It was a pretty smooth, gentle stop. So does 1 Newton or about 1 Newton make sense? I think so. It wasn't a lot of force. My fingers are fine. I probably should go wash them because of the bike tire. But generally speaking, that makes sense with the assumptions that we made. Now again, this is a straightforward kind of plug and chug. Can you find a force given some information? This is a pretty fairly basic, maybe like, and I'm thinking it's not so plug and chuggy because we got to find angular acceleration, but it's not an overly complicated single object system. If you're looking for a more challenging problem, or you've moved on from kind of these basic or more basic or average problems to an above average or two-body system, go watch the next video of the pulley and the bucket. That's more challenging. You're going to see we don't just need a net torque expression. You're going to see that we need actually net force and net torque to construct a system of equations and do some substitutions. So this is great. If once you have this hammered down, go watch the next video, figure out how to do two-body problems, and that will help you kind of start to see how forces and torques are related, how acceleration is linked to angular acceleration, and start building this complete picture of what motion is when objects move in lines and rotate together. It's fascinating stuff, kids. If you got questions, you drop in the comments, you send me an email. Until next time, see ya!